Welcome back to differential equations. In this video, I'm going to introduce you to the method of judicious guessing, which is a tool that will allow us to extend what we've talked about with homogeneous differential equations into non-homogeneous linear differential equations. Let me get my head out of the way and let's go through a quick review of some of that terminology. A homogeneous linear differential equation has some linear operator acting on some function and giving you zero. For the second order homogeneous linear ordinary differential equation with constant coefficients that has been the bulk of what we've talked about, we have that the linear operator L acting on y is sum A times y double prime plus B times y prime plus C times y. All right, nothing new going on there. That's the stuff we've been working on for a couple of lessons now. We have a linear differential equation. I'm looking at ones with constant coefficients because that's what we know how to solve. But as we build up tools for solving differential equations without constant coefficients, this idea will still hold true and still be viable. All right, so a linear homogeneous differential equation has the pieces like this. And a non-homogeneous linear ordinary differential equation has the same left-hand side, but on the right-hand side, instead of having zero, we have something. So assuming that y is a function of t, we have some other function of t over here. When we've been solving homogeneous linear differential equations, we've relied on the idea of superposition. If y1 and y2 both satisfy if I can write, L on y equals 0, then so does the linear combination C1y1 plus C2y2. I want to extend the idea of superposition just slightly. If I have some particular solution, y sub p, which satisfies the non-homogeneous differential equation, L on y is equal to f of t, and I have y sub h, the homogeneous solution, which satisfies L on y equals 0, then yh plus yp also satisfies L on y equals f of t. All right, that sounds like a theorem, so I guess I should probably prove that. And to prove that, we're going to use the fact that the linear operator is linear. L on yh plus yp is the same thing as L on yh plus L on yp. And L on yh is 0, L on yp is f of t, and 0 plus f of t is f of t. All right. Algebraically, that is really messy. There's a lot of dense notation that's going on here. So I want to summarize it in words. If our goal is to solve a non-homogeneous linear ordinary differential equation, we're going to break the process into two pieces. I am going to find the corresponding homogeneous equation, and I'm going to solve that. And I'm going to find the general solution. As we've seen in the past, the general solution is going to generally have two undetermined coefficients. For the second order case, it will have three unknown coefficients for the third order case, and so on. I'm going to take that general solution and I'm going to add to it any one particular solution to the non-homogeneous case. And if I can find that any one particular solution, adding them together will give me the general solution to the non-homogeneous case that we started with. Right. In this video, I'm going to show you how that works once you have at least some idea of the particular solution. And then in the next video, I'm going to go through and show you a little bit more of how we find that particular solution. So let's take a look at this differential equation. Y double prime plus 4y prime minus 2y equals 2t squared minus 3t plus 6. Implicitly, in this equation, we have y as a function of t. That's something that's worth noting before we do anything else. We have a linear differential equation. It's a second order linear differential equation. This left-hand side looks the same as the left-hand sides we've been dealing with for the past couple of lessons. The right-hand side, on the other hand, is a little bit different. It's non-zero. In this case, it is a polynomial. Right. So step one of this process is to solve the corresponding homogeneous equation. Take our left-hand side, set it equal to 0, and see what happens. We can solve this using the characteristic equation the same way we've been doing for a while now. Right, replace y double prime with c squared, replace y prime with c, replace y with c to the 0, which is just 1. We have the polynomial c squared plus 4c minus 2 equals 0. All right, that's a little bit messy, but we can deal with that. We could try to factor two things that multiply to -2 add to +4. I don't think exist. So I guess I'm going to turn pretty quickly to the quadratic formula. C equals the negative of 4 plus or minus the square root of 4 squared, which is 16, minus 4 times 1 times 2, I'm sorry, 4 times 1 times negative 2, which is minus negative 8, or just plus 8, all over 2 times 1, which is 2. All right, 16 plus 8 is 24. The square root of 24, 24 is 4 times 6, and 4 is a perfect square. And then the fraction reduces because we've got all these even factors. So we end up with negative 2 plus or minus the square root of 6. All right. So with that, we can write that the solution of the homogeneous corresponding equation, yh of t, is some constant c1 times e to the negative 2 plus square root of 6 t power, plus some other constant c2 times e to the negative 2 minus square root of 6 times t power. All right. Going through and doing all the stuff we did before, solving the homogeneous equation. Nothing has changed. It's just now it's only one step of the process. All right. I need the equation that we started with back. So I'm going to put a nice big box around this so that I can find it when I scroll back up again a little bit later. And I'm going to scroll back up again right now. Maybe. There we go. Settle down. I'm going to copy the original equation, which you probably still have within easy view and you don't need to rewrite it. But if you do, it's certainly not a bad thing. All right. Step 2 is to guess at one particular solution. Again, the next video in this series is going to be entirely how do we make this guess? But it is a guess. It's a judicious guess, hence the name of the video. The method is called judicious guessing. Sometimes it's called undetermined coefficients, because what we're going to do is we're going to guess that the solution looks like whatever's on the right-hand side, but instead of having constant coefficients, it has unknown coefficients. In our particular case, the right-hand side is a second-degree polynomial. And so I'm going to guess that my particular solution is a second-degree polynomial. Except I'm going to replace the coefficients, 2, negative 3, and 6, with unknown values a, b, and c. Right. This is probably the easiest one to understand. If the right-hand side is a polynomial, you are going to guess that the solution is a polynomial of the same degree. Let's talk a little bit about why I made that choice before I go in and use it. When I take the derivative of a function to get out a polynomial, I need to have taken the derivative of a function that was a polynomial 1 degree larger. Right? The derivative of a second-degree polynomial is a first-degree polynomial. The derivative of a first-degree polynomial is a constant polynomial. Going the other direction, the derivative of a third-degree polynomial is a second-degree polynomial. So I'm making the assumption here that if I start with a second-degree polynomial, I take its derivative and I get a first-degree polynomial, I take its derivative and I get a constant, well, then the thing that I have here is at most a second-degree polynomial. All right. So we know that this second-degree polynomial will take a form that could solve the differential equation. We just have to figure out what parameters we can put in, what coefficients we can use that actually does solve the differential equation, right? That's why it's called judicious guessing. We are guessing that a solution will take this form. Like I said, this process is also sometimes called undetermined coefficients because we wrote a function with a whole bunch of undetermined coefficients, and our goal is to try to figure them out. But from here, it's just a matter of take the derivatives and plug them in. If this is what yp looks like, then yp prime of t is going to be 2a times t plus b, and yp double prime of t is going to be 2a. And if I substitute those things into the differential equation, I will have 2a plus 4 times 2at plus b minus 2 times at squared plus bt plus c is equal to the right-hand side, 2t squared minus 3t plus 6. Right, slightly off the screen, so let me scroll up, make sure I got that right. 2t squared minus 3t plus 6. Okay, we're in business. All right. I can do some rearranging on the left-hand side. I can distribute and I can group together my t squareds, my t's, and my constants. Leaving us with a kind of ugly polynomial equation. Right? This isn't a trick that we use very often, but it is a trick you've seen before. We're not looking for a particular value of t that satisfies this equation. Kind of the opposite. We are looking for versions of these parameters so that this equation is true for every value of t. You've seen this logic in the past going through the method of partial fraction decomposition. And if you've taken a course in linear algebra in the past, you've seen this explained in quite a bit of detail. But for our purposes, we can set this up the same way. The only way that this polynomial will be true for every value of t is if the corresponding coefficients are the same. So in this case, that means that negative 2a is equal to 2, and that 8a minus 2b is equal to negative 3, and that 2a plus 4b minus 2c is equal to 6. That's a system of 3 linear equations in 3 unknowns. Right. As solving systems of equations goes, this one is actually pretty straightforward. This system is in what we call triangular form. If you take that first equation and just divide both sides by negative 2, you immediately get that a is negative 1. Then take that value of a and plug it into the second equation. 8 times negative 1 minus 2b is equal to negative 3. So b must be -5/2. Then take that value of b and the value we know of a, plug them into the third equation. And we get that c is -9. All right, now a bunch of backtracking. If I scroll up just a little bit here, I can remind myself that I was looking for a particular solution in this form. And now I know that a is -1, b is -5/2, c is -9, and that tells me that my particular solution doesn't need an extra stray mark, is going to be -t² minus 5/2 t minus 9. I'm not going to take the time to do so here, but I encourage you to take this solution that we came up with, take its derivatives, plug them back into the original differential equation, and verify for yourself that it does actually work and it satisfies the equation. What we care about right now, though, is that we have our particular solution, and if we scroll way back up to the thing that I put a box around earlier so that I could find it, sorry about that. I think that my touchscreen is possessed today. My controls are very finicky. All right. So we have our particular solution, we have our homogeneous solution. The general solution to the differential equation is just the sum of these two things. Y of t is equal to some constant c1 times e to the -2 plus square root of 6 t plus some other constant c2 times e to the -2 minus square root of 6 times t minus t squared minus 5/2 t minus 9. All that together gives us our particular solution. All right. Hopefully you agree with me. This process isn't short. It's a lengthy process, but it's not that bad. I'd like you to try something similar. In this differential equation, once again, it is a second order linear non-homogeneous ordinary differential equation with constant coefficients. The left-hand side you can deal with. You can find the homogeneous corresponding solution. The right-hand side involves cosine. All right. So I will give you the lead here. Again, I'll talk in the next video about how to determine what kind of particular solution to guess. But for this one, I'm just going to give you that you should guess that the particular solution is going to involve sines and cosines of the same argument we have, 2t. So let's guess that the particular solution is some constant a times the sine of 2t plus some other constant b times the cosine of 2t, and take a few minutes, see what you can get out of that one. I forgot to put down instructions. Right? Find the general solution. Take a few minutes, see what you can do in trying to find the general solution following the same sort of procedure we used on that last problem, and I'll see you in the next video.